So he's the first person to propose that matter was composed of tiny particles called atoms. Called them atomos in Greek. He believed that atoms could not be created, destroyed, couldn't divide them. He also believed there was an infinite number of different kinds of atoms. So everything around us is a unique type of atom. Now, raise your hands if you agree with him. Can you guys agree on at least a few parts of it? Yeah. What do you agree with? Tyson?
That they cannot be created, destroyed, or divided.
That's basically the law of conservation of mass, isn't it? We'll get to the divided a little later. I get people, wait, divided? Wait, we'll get there in just a little bit. Okay? Created or destroyed, yeah, that's basically the law of conservation of mass, which we've already talked about. Okay? Is everything made out of tiny little bits of things? Yeah. He thought that they were like exactly like the whole, like water kind of looked like water down below, like a tiny little bit of water, or cheese would look like tiny little cheese wedges. That's not necessarily true, but we do have tiny little bits of water, right? We just call them little water molecules, and they look like little Mickey Mouses, right? So they don't quite look like water, but the idea is still there. Okay? Now, there's not an infinite number of different kinds of atoms. But there sort of is. You can take atoms and combine them to make compounds. We learned about that in chapter 3. So he didn't really have the idea of atoms versus compounds. He just thought every material was a unique thing, a unique atom. We now know that we got atoms and then we got compounds, which are combinations of those atoms. You could combine them in any possible way. There's infinite ways to combine them. Some of them don't work, but literally, you can combine any of the 118 elements all sorts of ways and create like an infinite number. Does that make sense? Especially when you get to carbon, because carbon can do almost an infinite number by itself with other elements. Carbon's a unique one. So yeah, that is kind of true. Here's what he thought atoms looked like, and I want you guys to take the markers and draw this. Little mini versions of the whole thing. So water, he pictured that as like tiny little spherical water droplets that were slippery. So they'd slide around past each other. He thought of iron as tiny little chunks of iron, and they were spiky. Why do you guys think he thought they were spiky? Yeah.
Because it doesn't like move.
It doesn't move. Like iron is hard, and it's hard to break. Like everything about iron is hard, and it's hard to break, and they don't want to move. So he thought, okay, that maybe they have spikes on them. That'll get them like stick together like Velcro, and they're not going to move that way. Like it makes a really hard substance. Stone, he pictured as tiny little bits of stone. Fur, tiny little furs that get together and make a larger fur. So you can take a piece of fur and cut it into smaller pieces. There's got to be tiny little bits of fur there. Now, he was a philosopher. That means he was not a scientist. He had absolutely no evidence for this idea, besides just looking around at the world and what he could see, and he's coming up with this idea. He said, this kind of makes sense with the way I see things, but he didn't really have any evidence for it. Not science, really, but he was on the right track. Okay, we ready? Now, it took a long time for this idea to catch on. The reason why is this guy, Aristotle. You guys heard of him? You guys heard of Aristotle?
Yes.
Okay. Most people have heard of Aristotle, but not Democritus. That's because Aristotle is famous. It's his idea that caught on. Democritus' idea did not, but Aristotle's idea did. His idea is that everything's actually made of some combination of 5 elements. Earth, fire, air, water, and ether.
What's that?
So ether is what they believed things in the sky were made of. Like the moon and stars and the sun. So ether had a unique property of being able to float. So they thought, okay, the moon has earth and ether in it, and that's why the moon is floating up in the sky and not falling down to the earth.
Is the moon flat?
So, no. Anything with ether in it would then be up in the heavens, up in the sky, and not actually on earth. So when we're talking about materials on earth, they usually stuck to the first four: earth, fire, air, and water. They didn't usually have ether. In fact, how many of you guys have ever heard of ether before then? A couple of times, but... How many of you guys have heard of the earth, fire, air, water? Yeah. So,
Fire Nation.
that is very common in popular culture because this idea was around for so long. I mean, it's just in our popular culture, in our movies, in our books, everything like that. We still have it around. Just it's fun. You guys like Airbender?
Yeah. Oh, yeah.
Yeah, they do this too. Yep. Earth, fire, air, water. Hey, you guys ever watch the movie The Fifth Element?
Yes.
I watched the last.
They've got the four elements, and then they said the fifth element was like humanity or something like
The
that.
supernatural being.
So, yeah.
I think it was.
But, anyways, it prevailed for 2,000 years. Now, just as a summary here of what this idea is, every object, every material is made of these things, and it's a combination of those things that make the material what it is. Okay? All living things are complicated, and so all living things actually had all four things in them. That had earth, fire, air, and water in a living thing. We know we need to drink water, so that's in there. Okay? We had a little earth in there. We have to breathe, so air is in there. And fire was kind of like the spark of life.
Oh, okay.
Yeah.
Why is there fire in
So fire was like, hey, it's gotta have, if it's got like a spark of life in there. By the way, living things, since they have all four, they're like, well, if you burn a living thing, and literally anything that's dead, that was alive and died, you could burn. I guess all of it could burn. You could actually then break it apart into its four elements. That's what they were seeing when they burn stuff. They're like, well, the fire is released when you burn it. Then you get smoke coming out. There's the air. And then you guys ever seen bubbling on like a log? Mm-hmm. We know there's water in living things, so bubbling on the log. And then what's left is charcoal, ash, which is earth. So the little tiny little bit of earth there. That's what's left. So that's the basic idea behind this. Is it right? No. I think Democritus is a lot more right than Aristotle. Okay? But there is one element of this that does work. That Democritus didn't get. Let me go back a slide. 2 slides. Infinite number of different kinds of atoms. That's not true, is it? 5 things. Closer to the truth. We now know there's 118. Everybody follow that? So, besides the elements themselves, the fact that things are made of specific, limited amounts of things, this is where that idea comes from, and it's still considered true. Okay? Still considered true. So this idea prevailed for 2,000 years. Democritus kind of got forgotten for a while. Then we get to the Middle Ages, and we come across alchemists. 12th century to about 18th century. It developed in the Arab world, in the Middle East, and then it moved on to Europe. These were what I would consider the first scientists. Put little quotes around that. Scientists. They were kind of like pre-scientists or pseudo-scientists. They were, in fact, experimenting. But at the same time, they weren't really experimenting very well. They were tinkering, I guess you could say. They focused on purifying things, extending life, transmutation, which is what they called turning one thing into another. It was their goal is to turn stuff into other things. I mean, essentially they were actually doing that. They were doing chemical reactions. And like, hey, I'm turning this into that. I'm turning it, I'm transmuting it. But there were other things they couldn't transmute, like gold. It's because gold's an element. Most of them were actually like greedy people. They were crooks. Some of them were trying to live forever. They wanted to be immortal. You guys ever heard of the Philosopher's Stone?
Yes.
That is a true thing that they thought they were trying to find. It was like, let's find the Philosopher's Stone. It's like a mystical goal that they had. Create a material or an elixir of life that would let you live forever. Now, some alchemists actually developed into doctors. Because as they were trying to find, they actually did things that help people live longer. So that some of them kind of developed into doctors, but some of them were just trying to get rich cheap, or get rich quick. So they're like, let's take a rock and see if we can turn it into gold. Some of them were actually like very sneaky crooks, because they would take a rock and they'd spray paint it gold, but not spray paint, but they paint it gold and they'd be like, look, gold! And then everybody would believe them until they skipped town. And they're like, wait, this isn't gold, it's just painted gold. That happened a lot. Somebody claimed they turned something to gold, it's usually because they painted it with gold. Took a little bit of gold paint and slapped it on there. So there were elements of magic, mysticism, but they did carefully study materials, and this is where we started to actually develop chemistry. Because we're looking at different materials, we're learning about them, even if the intentions weren't really like there and they weren't very good at experimenting, but elements still embraced, a lot more than them. They also started thinking again about Democritus' idea of the atom. Eventually, this turned into chemistry. It's hard to put an exact point when alchemy became chemistry, but you can see the shift in the names. Like the names are similar. Alchemy turned into chemistry. Chemistry is considered a science, and this is like a pre-science or pseudoscience, if you will. Okay. FYI, here's an old list of elements that they had. Now, they listed the heavenly bodies like the moon, the sun, and the earth as elements. Okay? But they do have a couple elements on there. You guys see copper, lead, arsenic, phosphorus. So there are some on there. They still got the old elements, earth, fire, air, and water. They're up there. Don't ask, I don't know why lead's on there twice. Salt's on there twice. Salt's not an element, though. But they thought it was.
White lead.
White lead, what's the difference between lead and white lead? I don't know. But
One is
They
white.
put that
One's
painted white. Guys.
yeah.
Olive
Painted.
oil. White, not white lead.
But it's just sort of a list of elements that they were kind of coming up with at the time.
Vinegar.
Vinegar, apparently.
Oil.
Yep. All right. So Antoine Lavoisier is considered the father of modern chemistry. He's the guy who's like, hey, we're alchemists, and kind of turned it into an actual science, turned it into chemistry. He insisted on very careful measurements of everything, and you had to have evidence to support your ideas. He wasn't the only one at the time who was coming up with this, but he was the one for chemistry. There were other scientists in physics that were coming up with similar thoughts on having evidence to support ideas. He did a lot. Now, he made a joke in that little video, guys. How many of you guys have ever thought, man, chemistry, the guy who invented this should be put to death? That's funny. Yeah. I'm like, you guys have done enough chemistry by now. I mean, you should probably have thought that. It was. But it was because of the French Revolution, not because of he was invented chemistry. He helped define an element in a compound. We have elements, they combine and they make compounds. Combining to make compounds is where the name comes from. He got rid of some of the ancient ideas like 5 elements. There's more than 5 elements. Fire's not something, it's a process. He did a lot of work with fire. Did you guys pick up on that?
Mm-hmm.
He did a lot of work about fire, so most of what we know about fire kind of comes from some of his work. Alright? I'll get into more detail on that in a second, but he actually broke water apart into hydrogen and oxygen, proving that that's not an element. Oxygen, he discovered. He actually discovered oxygen. Well, he was one of the ones who discovered oxygen. There were a couple other people working on it that didn't realize it was oxygen. I think it's funny that he actually discovered different types of air. He realized the air around us is made of more than just one thing. Up till now, it was just air. We breathe it. We need it. But he was getting into like, oh, there's different types of airs. Called them all sorts of weird names, but they all had air in them. Fixed air, phlogistonated air, all sorts of things. Okay? I got 3 slides on him. Ready? Are we ready on this slide?
Yes.
Okay. No? I heard a no. Okay. He came up with the law of conservation of mass. That's his. Used to be called Lavoisier's law. Matter may change its form or shape, but the mass will always remain the same. He helped construct the metric system. This was during the French Revolution. He was actually a part of that, although he didn't finish it because he was killed during the French Revolution. Ready? He helped discover a lot of elements. He discovered oxygen, hydrogen, nitrogen, phosphorus, sulfur. Since he kind of defined what an element was, instead of just the 5 elements, he categorized mercury, zinc, gold, those as elements, a couple other things. He disproved the idea of phlogiston. Now, when I say, and I start off with, he disproved phlogiston, you guys are going to be like, okay, so phlogiston, don't care what it is, but it's not true. Let's talk for a minute about why phlogiston was a big idea. What happens when you burn something?
It dies.
Take a log and burn it. It's already dead. What happens to it?
Turns to ash.
It turns to ash and goes away, right? So the idea here is that, okay, well, we have this element called phlogiston. It was on the periodic table for a while. So we have phlogiston as an element, and things that burn have phlogiston in them. And fire is phlogiston escaping. That's what fire is. That's the idea. Which is a little more scientific than Aristotle's idea. But fire is phlogiston escaping. You got 2 things. One of them is kind of escaping and going away. Now, if you don't call it phlogiston, if I just said, oh, I have a log, and it's made of several things, and when I burn it, one of those things is escaping. Does the idea kind of sound good? Yeah? Is that really what's happening, though?
No.
We kind of already talked about fire. What is actually happening with fire? It's turning into something else. It's not breaking apart and phlogiston going away or something going away. It's oxygen in the air binding to it, turning into something else, and then it goes away. So it's not all contained in there. Air is a part of it. You guys see that? The idea with phlogiston is that air is not a part of it. Like, they weren't taking air into account at all. They weren't taking the oxygen into, because they didn't know what oxygen was. So it's not losing phlogiston, it's actually gaining oxygen. Does everything, when you burn it, lose weight, lose mass? What about the steel wool last week? No. Not everything loses mass when you burn it. Some things will actually gain mass. That's because when you burn it, you gain oxygen. When you burn a log, it gains oxygen as well. It just turns into something that is a gas, so the gas goes away. But it does actually get heavier when you burn it. It just floats away. If you catch it, it would be heavier. We just don't normally catch it. Yeah?
So did people back then believe that you could set fire on fire?
All right. So, I've got another video for you. Now, please ignore the formulas. He came up with the formulas after. Like, now we're like, that's what it is. But this is what he did. He said, okay, so if I take this much nitrogen and that much oxygen and I get a compound, and the same amount of nitrogen and that much oxygen, I get a different compound. And this much and that much, I get a different compound. I get 3 different substances. What he noticed here is that they're all related by exactly whole numbers. That is double that. This is double that. This is double that. Everybody see that? Perfectly. It worked out for so many different compounds. So he is having evidence here that shows that matter is actually composed of a discrete chunk. There is some undividable thing, like Democritus said. So we have equal amounts of the nitrogen and oxygen here to combine, double the oxygen there, double the nitrogen here. Can we follow that? He's basically proving atoms exist. John Dalton, he was an English school teacher. 1800-ish. Unlike Democritus, he performed experiments which allowed him to show that Democritus was right. Things are made out of discrete little bits of material, which are called atoms. He just went that little bit further, and like you can combine them to make compounds, like Lavoisier said. So he came up with the atomic theory. Like bold letters here. The atomic theory. Here it is. The atomic theory. First part. All matter is made up of particles called atoms. Next. All atoms of a given element are identical. Next. Atoms cannot be created or destroyed or divided. This is essentially the conservation of mass. And it goes back to Democritus and Lavoisier. Lavoisier sort of proved this with his experiments. Can't be created or destroyed. And lastly, atoms combine in simple whole number ratios. That means 1 and 2 and 3. Whole numbers, simple ones, to form compounds. This is the law of definite proportions. Water is always H2O, 2 hydrogens to an oxygen. Carbon dioxide is always CO2, 2 oxygens to a carbon. Ammonia is always NH3, 1 nitrogen to 3 hydrogens. Simple, nice, easy numbers. Perfect proportions here. But they can be rearranged to make new compounds. They react and they rearrange and they make new compounds. None of the material is lost. This is what we were doing last week. We're talking about chemical reactions. This is the atomic theory. For the most part, this is still true. That's why I'm giving it to you. But we might want to put like a little asterisk next to some of these. How many of you guys think you know which one we need to put an asterisk next to? You were right. The second one, all atoms of a given element are identical. It is true that all atoms of a given element will react the same and create the same materials. But that doesn't mean they're identical. Okay? We're going to talk on Friday about how same element, they could actually be different. Okay? There's just very subtle differences from atom to atom sometimes. Even though they're both like, say, carbon. 2 atoms will still be carbon, they still react like carbon, they still make compounds that carbon makes, same compounds. So for practical purposes, they are identical, but there are tiny little differences. They're called isotopes. The other one is the third one. Atoms cannot be created, destroyed, or divided. Can you divide an atom?
Yeah.
Yes. Splitting the atom? You heard of that one? That's what happens in an atomic bomb. Or in a nuclear power plant, which is basically an atomic bomb scaled way, way down to be nice and slow so we can get power out of it. Are you guys constructing an atomic bomb?
Yes.
Right now, in this room?
No.
No.
Yes.
No.
Are you going to be working in a nuclear power plant?
Maybe.
Maybe. I don't know. If you're not doing literally one of those two things, you're not dividing atoms. Most people are not going to be doing those things. So for all practical purposes, can you really divide atoms?
Yes.
Not really. In this room, we're not going to divide any atoms.
Aw.
We're never going to divide any atoms because I don't want to be setting off a nuclear bomb. I'm sorry. Okay? So no dividing of atoms in most of your life. 99% of your life, 99.9% of like everything, they're not dividing. Right? So practicality, that one is true most of the time. It's just very specific instances where it's not. Yeah?
So why are nuclear bombs and nuclear power plants so...
So Dalton's model of the atom, he pictured atoms as little circles, just like we were drawing last week. He pictured as little spheres. Okay? You didn't think you could divide them, so it's just a little sphere. They combine to make compounds. This is what we were doing last week. This is a perfectly acceptable model.
So thought copper had a C in the middle of it.
Now, this picture over here is how he drew them. This is like a chart that he drew. They didn't have markers really back then. Like they had pens and things like that. They didn't really have colored things. Color was kind of expensive and rare. So instead of color coding them, they would usually symbolize it. So he would make different symbols to make them look differently, which some of you guys do when you only have a pencil. How many of you guys have made little different symbols and things? Usually you just write the letter or something in the circle, right? That's what he was doing. So he's got like hydrogen, circle with a dot. Copper was circle with a C. Sulfur was circle with a cross. Things like that. Okay? Now we just color code it because markers are easy. They're cheap. Yeah?
Yeah.
Was he wrong?
Not necessarily.
Not necessarily. It's a good way to think about it. Democritus is a good way to think about it sometimes as well. This is a little bit more detailed than Democritus, though. So he's not wrong. Does he have the whole picture, though?
No.
No.
Let's put
Not a single mention of electron, proton, or neutron, right?
Let's put Tina.
So we've got more to go. Sound good?